Good evening, engineers. I hope you're doing well. Gatimo Ithaka over here, and I'll be your host for today's session as well. So, unfortunately, during the previous session, I wasn't able to save the recording, so it kinda got messed up, and I was not able to share it. But due to that, we are going to be having a recap on the class that we had last time, and you're also going to go a step further and do our analysis today. Okay. But before we get there, I'd like to get your thoughts on two things. Uh, there are there are two things that have just come to my mind that we did not cover. So I would want to get your thoughts. Should we handle the flat roof? Okay. Because number one, the wall will not be 3 meters high. Not all beams are going to be loaded with walls because the area is supposed to be open. And then number two, what if we assumed the flat roof is going to be a storage area for the water tanks, which usually happens? How would you handle that? Anyone willing to share?
I'm sorry, Coach. I didn't hear your question.
Pardon?
I didn't understand your question.
Okay, let me repeat. So we've been talking about loading for quite some time, and now you understand as what loading is and probably why we are loading our structure. So I am pointing out a scenario that you are likely to meet on site. The first one is the beams on the roof level. So if you look at most or on all concrete structures, we do not have when we have a flat roof, we do not have walls going above the flat roof, right? We usually have just a tiny wall, probably a meter high maximum, and then some grills. All right. So how would you handle that in robot? And then number two is in the scenario where the flat roof houses or is used as a storage area for your tanks. How would you handle that?
I have understood the question, but to be honest, I don't know how. Maybe for the tanks, maybe you can try to calculate the weight of the tank and maybe come up with the logic, but I don't know how you can enter the logic in robot.
Okay, good. Good. Thank you for sharing, Melissa.
Hello, Captain.
Hello, engineer. How do you do?
Fine, I'm good. And you?
I'm well.
Okay. Considering the first one, which is when we have a, like, let me say 1.5 meter high block on top of the either the slab, the roof slab, or the beam, probably.
Yeah,
So since we know the unit weight of the block, the load bearing block,
yeah,
then
yeah,
we multiply it by the height and the
yeah,
thickness of the block. So it will give us
yeah,
the load. So, and it is also a dead load.
yeah.
So we
Okay.
have to highlight, we highlight the we highlight it from the object inspector, then we will load it with member selection and the likes. But the
Yeah.
aspect of the water retaining structures, whether water, what do we call it, storage for saving waters, then we have to know the storage capacity of the tank. So from the storage capacity of the tank, and we know that the unit weight of water, as you said, if you are using kilonewton per meter cube, is 9.81, and if you are using kilogram per meter cube, you said we should add 50, which is 1050. So from there, we just do the dimensional analysis calculation for it, and we achieve
Yes.
our. Then it's also part of dead load, not as point load, not as live load. I don't know
Okay.
if I get the question
Uh,
right.
I think that's a good way to approach it. But on most cases, when it comes to the storage areas for the water tanks, we usually try and use the live load so that we can have, say, a larger factor of safety, because sometimes you may not be able to foretell what the clients will do. They may tell you that they're going to use a 10,000 liter tank, but later on they decide to use a 15,000 or even a larger one. So just to be safe, I'd recommend for the water tank, because it is likely to change a lot. You you use the live load.
Captain, James here. I think the other reason
Hello,
for making
James.
it, yes, the other reason for considering the load of the water as a live load is the fact that the tank will not always be full. The content of the quantity of water will fluctuate with time. And that to
Yes.
me is characteristic of a live load. So the danger in assuming it dead is that, sometimes the worst case scenario is not necessarily when you have maximum load. It's not necessarily the worst case scenario. Those fluctuations can actually sometimes lead to worse case scenarios, worse in quotes, than when you have full loading all through. So there
Yeah.
is that tendency to think that once it's fully loaded, that is my worst case scenario. But it's not necessarily the case. It's kind of counterintuitive, but yeah, it is actually the case. So I would consider it as live due to the fact that the water levels will fluctuate.
Yeah, actually, thank you for that, James. You've actually reminded me of something that I'd also like to highlight. So when you're doing your water retaining structures, such as your underground swimming pools, you need to have two types of uh, ULS loads. Okay, the first one is when the swimming pool or the water retaining structure is completely empty, and then the second one is when it is completely full. All right. So the reason we consider when it is completely empty is because there's not going to be water pressure from inside of the wall pushing on the outside of the wall, so that there is a bit of, say, canceling out between the soil on the outside of the wall and the water pressure on the inside. So when you calculate when it is empty, you get to see which one is the worst case scenario and then get to design for that. So thank you, James, for your point. I think it reminded me of that, and it was just proper I brought it out. All right, so someone else, please feel free to share. Feel free to share as we wait for a few more members to join us. So for those who joined us late, this is what we are discussing. So for most concrete structures, you're going to find that when you have a flat roof, you do not have walls going above the roof. Okay, and then at that particular level, not all beams are loaded. Okay, probably only the outer wall, only the outer beams are loaded. So we may need to account for that. And then the other thing that you may want to account for is the scenario where the top slab is used as a storage area for your water tanks. Say you have 10,000 liter plastic tanks. How do you account for those loads on the slab? Anyone else? Anyone else willing to add in or just share their thoughts with regards to that before we start presenting?
Yeah, a quick question on back to the water tank scenario.
Yeah.
So in that case, when we are doing the loading, do you because you may not for sure tell, clients are funny, like you said, you not for sure
Mm.
tell which part exactly they'll load. So do you just load the entire roof with that, or do you like how would you treat that, the addition of the live load? Do you do it for certain panels or you do it for the entire slab? In which case it would kind of like be very expensive, but also sometimes you'd rather err on safety than try and have an economical design which is going to fail. So how exactly do you add that live load on the roof slab?
Okay. It depends. You've mentioned the two cases. So it depends on if you're going to be involved throughout the construction of the project. So if you're involved throughout, you can be able to say control where the tanks are stored. So during the design phase, you could load the specific slabs. Okay. But in the case where you're not going to be in control of where the tanks are placed, I just prefer or advise you design the entire panel with the tank loads. Okay, except where they are using them as hanging lines. So for those particular panels, you could avoid them. But if you're not in control, I think the safest option is to just load the entire floor with the tank loads, so that you are safe. You are safe in case the client does whatever they may do, or in case of any eventuality. All right. So I think with that, I'd like to start today's session. So we're going to start from where we started off last time. Sorry for that once again. So I'll share my screen. If you can see my screen, please type a 1. Let me know that it is visible. Also, if I'm audible, type a 1. Let me know that we are together. Super. So, okay, so let me close this and then start. So in the previous class, we were able to have no warnings. That's good. So in the previous class, we started with modeling the foundation walls. So we said that our structure is a 5-story structure with a basement floor. So for the basement floor, we expect to have soil acting from the outside, pushing the wall inside. And we need this wall to be able to resist those loads. Okay. So we are going to start with modeling the foundation walls or the basement walls and then load them. So I will recommend you do this. Okay. I'll recommend you do this in this same way. So what I will do is I will go to my foundation, to my walls here. All right. I'll go to my walls here and then I will define a thickness. Okay, so defining a thickness follows the same thing that you've been doing for your panels. So I'll just type here, say, basement walls, and then I will enter a thickness of 200 mm, and then I'll just click on add. And then once I do that, ensure that in the thickness, that is the one that is being used, the basement walls. And then in the height, I could always take care of this. If you are using a 3-meter height, ensure it is 3 meters here. If you are using a different height, you can add that here. So I'll start modeling these walls. I'll just start from the bottom, and then I will click at the column centers. So the reason I'm doing this, the reason I'm modeling to the column centers is so that some of the lateral load is transferred to the column as well. Okay. So if you say snap at this column face and then continue your wall from this column face going upwards, your columns are not going to be designed, or your foundation columns are not going to be designed to resist those lateral forces. So for you to ensure that they are accounted for in the column design for that particular level, I recommend you do this. Just model them to the column midpoints so that it is easy so that the software is able to consider them in the design. Okay, so that's all you need to do. And then I can press escape. And then once I do that, if I go to my view plan, if I go to my view, I should see my currently modeled. I don't understand. Okay, since they were not modeled, let me redo that quickly. Or is my software acting up? Okay, so let me just redo that on the other end. We see if they are going to be modeled. Okay, so I think there is something wrong. I think there is something wrong there. So let me just close the software and then restart it. Yeah, so I will just proceed from where we left off. So I want to start modeling from story one, and then I will just go to my walls. I will use the thickness that we had previously used, and then in the height, ensure it is 3 meters, okay? 3 meters, or let it be the same height as your floor level, and then model them, the column centers. Why is this happening? You really don't understand what is happening there. Let me retry that. Go to my walls. I'll define a new section. Okay. I don't know why my software was acting up before, but I think now we are good. So I'll just proceed. So ensure you're modeling in the story one, and then you define your section correctly. Ensure that the height is 3 meters, and then you click on this point to start modeling, and then proceed to model from column center to column center. Okay. And then as you do that, the thickness should appear here. So continue to model. Okay, so continue to model. Let me uncheck that. Then turn on drag so that you can make it easy. Turn on drag so that you can make it easy. And then just proceed to snap upwards. Okay, continue to model through the column midpoints. And the reason we are doing this, the reason we are snapping within the column is so that the column or the load, the lateral loads from the soil are also included, or they are factored in the design of these basement columns. Okay, so if you place your walls to the face of the column, they are not going to be considered. So just to be safe, ensure you model them to the center of the column and proceed and turn on drag, proceed all the way to the end. And then once you are at the top, just continue modeling. Model them throughout the entire perimeter or outer perimeter of the structure. Okay. Continue clicking on the nodes. And then I will recommend that you model from top to bottom. Just recommend you model from top to bottom. So let's proceed. So for this one, I'll model from this point to this point. And I'm doing this just to control the local axis. So model them from bottom to top, okay? Model them from the bottom part of your structure, or from axis 1 or axis 0 going upwards, just to be in control of the local axis. Okay, so let's do that. Let's do that, and then that up to that end there, right? And then press escape. If you had turned on drag, press escape, and then finish modeling this particular face over here. Okay, so once you are done, you could press escape and close. Okay. Then you can go to your view plan to see it in 3D. I recommend you do this in 3D so that you can see them here. Okay, go to your 3D and you're going to see your basement walls there. So modeling them is that easy. So the next thing that we want to do is to load them. And then we said the first step of making or inputting any loads in the software is listing it or creating a type for it. So to create a type for this, you go to loads and then you go to load types. So let's create a type. So you go to load types. For the soil loads, they are not going to be changing a lot. So we're going to use them as dead loads. And then you're going to add here soil loads. All right. And then once you add them, just click on add and close. Okay, so let's start with the soil loads. So in the list, ensure soil loads are the ones that are, ensure that the soil loads are the ones that are active. And then before you go to model the loads, I'd recommend you do this. Select the basement walls and view them in a different window so that you do not see the entire structure, so that it's easy to work with them. So to select the soil the basement walls alone, you use the member selection over here. You use the member selection. Then you go to panel and you change this to basement walls. Click on the walls, select the basement walls. So click on them, then click on these two arrows. Then once you click on them, click on edit a new window so that you can view them alone. All right. And then once you get here, I'd like to just repeat on what we covered last time. So every section in robot has a local axis, and we have the global axis. So the global axis is what you see here. Z is the change, say, from the base up to the going upwards, say up to the roof level. And then X is from left to right. And then Y, if you are looking at it from the plan view, is this direction here. Okay. So that's the difference. So Z is in the elevation view, X is from left to right, and then Y is from bottom to top, or from your grid 1 to the final grid 17. All right, so that is the global axis. And then from the global axis, now each member has its own local axis. Okay, so I want you to assume that this is the width of the wall, and then this is the height of the wall. So this would be, say, 3 meters, and then this is something like 3.5 meters. Say this is the distance between a grid here and a grid here, and then this is the difference in elevation. So this is our basement, and then this is our story 1. And then right next to it, I will draw a section view. Okay, so this is the thickness of the wall, the 200 mm. Okay, so I hope you're together up to there. So in the local axis, this is our direction X. Okay, and then this is our direction, or this is our axis Y. Okay, and then in the local axis, this is our axis Z. All right, so this is X, this is Y, and then the thickness is the Z. All right, so if we are together there, please type a 1 so that I can proceed. If we understood the local axis, please type a 1. Okay, so I'll proceed so I can see we are good. So now from there, we can define the soil loads because they are dependent on the application is dependent on the local axis. So to view the local axis, you just go to these options over here, just below the global axis. Once you click on these options over here, you have the local systems. So click on them once and you can be able to see the local systems. So once you click on the local systems, you can see the axis we've been talking about. So y is in green, so this is y. Then blue is the X. You can see X here. X is in blue. And then red is the Z. And each panel has its own local axis. So the reason I was trying to ensure that we model these panels from bottom of your screen going upwards is so that these local axes remain uniform. So if you look at my panels, all my local axes are going in the same direction. So that is what I was trying to achieve. Okay, this is what I was going for. Okay, because it may become a little difficult if you tried to model your loads and your axes are in different directions. It means you'd have to do, say, some panels in a certain way and then the others in a certain way. So it becomes a bit troublesome or tedious. But if you follow just how we model them, it will become a bit easier for you. So now that you understand the local axis, I want you to do this. You're going to go to loads and then you're going to go to special loads. So the soil loads are under special loads. So you just go to special loads and then you click on soil pressure. And then once you are here, the first thing that you're going to do is you're going to click on parameters just to set the type of soil. And setting this is really easy because all you have to do is either type in the type of soil that you are using or use an available type of soil here. So I'll just go with clay fine sands here, and then I will enter my base level height. So I'll enter it as 3 meters. All right. Then once I enter that as 3 meters, I will go to loads and then results and just click on apply. Then once I do that, now I need to select my panels. Okay. So I need to select my panels. So before I select my panels, I'd want to show you something else. Okay, let me open a new one. So assuming this is our wall here, and we have our loads acting on the soil, so we expect the load distribution or the pressure distribution to look something like this. Okay, you'd expect your pressure distribution to look like this. So you expect your loads from the soil to be distributed in such a manner. So you have a triangle. The minimum point is here, and then the maximum is here. So I think the formula for calculating this is usually same. The pressure is equals to, say, the active pressure times the density of the soil times the depth. So if you have, say, your active pressure coefficient as, say, as a unit, okay, or as something that is standard, so you expect that if this is going to be 0 because you do not have any increase in depth, and then as you go towards the lowest point of your wall, you expect your maximum pressure to be here. So if you join it, you expect that your load distribution would look like this. So we want to ensure that whatever we model actually makes sense. We do not want to be in a position where the soil distribution looks like this, number one. So let me do something here. So where's my errors? Do I know how to use this thing? Okay, so this is the ideal situation where this is the inside part of the wall, and then this is the outside of the wall. So the soil is here. So we want to ensure that our pressure is pushing the wall inside. So there are things that I want us to avoid. Okay. There are things that I want us to avoid. The first one, this is the first thing that I want us to avoid. The first thing that I want us to avoid is this, having your pressure. Okay. The first thing that I want us to avoid is this. I want you to avoid having your pressure acting on the inside of the wall. Okay, so the left side is the inside of the wall, and then this one is the outside part of the wall, just for this demonstration. So I want us to ensure that our pressure is pushing the wall inside, okay, just like this. Then the other thing that I want us to avoid that you may find happening from time to time. So if you define this wrongly, you're going to find yourself in a situation where the software will define the load in this manner. Okay, you're going to find yourself in a situation where the software will define, you're going to find yourself in a scenario where the software may give you such a scenario for your load distribution. So you're going to see that this is quite wrong because it is suggesting that you have your lowest pressure here and your maximum pressure at the top, which is misleading. Okay, and then this will also give you erroneous results because if you remember correctly, the maximum pressure from this soil will be acting at a third. The effective area of this shape is usually at a third from this point here, or 2/3 from this point here. So in this particular scenario, you'd expect the say the pressure to be done to at such a point here. Okay, so if you calculate the moments for this, it will be larger than the moment if this pressure here, or this force, is at this particular point here. Okay, as it should be, because it should be 2/3 from this 2/3 from this point of the triangle and a third from the right end of the triangle. So if your load is distributed in such a manner, it means that your moment is going to be your force is going to be multiplied by 2/3 the length of the wall, which may be misleading and it may lead to an over design. So that's what I want us to avoid. So we are going to do this panel by panel. Say these panels here, then this one, then this one, then this one, just procedurally to ensure that we define them correct. So after you have entered your parameters, you've entered the type of soil and the level. So you just click on loads, results, and then you apply it. Then once you do that, you go to, you ensure it's under panels. So panels is checked, and then you click on the list of members to select them. Ensure this is highlighted. And then once you ensure this is highlighted, just take note of the load direction. We have according to local surface system and opposite to local surface system. So you don't need to cram this. We are going to use them interchangeably depending on how the soil pressure has been distributed. So to make this a bit easier, I don't want you to cram this. I just want you to be able to understand what the software has modeled. And then if it has done it wrongly, you just undo, and then you select a different load direction. So I will start with member selection. I'll select these panels here, then press Control and select these panels in this direction here. Okay. So let me do that in a really easy manner, and then you apply the loads. So once I do this, you can see how this load has been distributed. You can see it has been distributed in the manner that you are describing as ideal. You can see that you have your maximum pressure at the bottom and your minimum pressure at the top. And then the load has been done on the correct side of the walls because this is the outside part of the structure and then this one is the inside. So we want our pressure to move the wall inside. Okay, so that one has been done correctly. So I'll just press escape, then go and select this, go to loads again, load definition, ensure soil loads is still the active case, not load definition, sorry. You go to special loads and then soil pressure. Then once you get here, just rotate with the view cube and then proceed to select these walls. So the parameters are still set, no need to set them. So there are no need to set them. So all you need to do is now click on the list of objects, then select this wall, select this one, select this one, and select this one. So I've still not changed the load direction. I'm using it as it was before, and then I will apply. So once I apply, this one has also been done correctly. Okay, you can see that the load has been distributed correctly. So once this has been done, I'll just delete this. Sorry, I should have applied first. So you click on apply first and then you delete them. Then after you delete them, you proceed to do the other walls. So you just use the view cube to rotate. Then you select these walls here. I first click on escape so that you unselect the walls. Then select this one. Then select this one, this one, this one, this one, this one, and this one are in the same direction. Then just apply. Okay, so we have that. Okay, so you can see if I show this direction, you can see where the load has been added. You can see where the load has been added. It is acting in this direction here. So it is pushing our wall outside, which is an ideal. So once you get to that point, just undo until this load here disappears. Okay, just undo it a couple of times until the loads for this wall disappears. And then once you ensure that it is not there, so undoing it is literally the easiest thing that you can do. So once you ensure that it is not there, just press escape to ensure these walls are not selected. Go to parameters, just go to results and apply. And then when you come to select your members, and then select these panels here. Okay, so select them, and then this time in the load direction, change it from opposite to local surface system and according to local surface system. So just interchange them and then click on apply. And then once you do that, you notice that the load is now applied correctly. Okay, you're going to notice that the load is applied correctly. And then once that happens, just click on apply once and then undo this. Then press escape to unselect these walls. If you are taken out of the load definition, just go back. Sorry, I keep going to load definition. You go to special loads and then cell pressure. Go to parameters. You've already set the parameters at this point, so I'll just click on apply and close. Then click on list of objects and then select your walls. And then just click on apply. And then once you do that, you see that your loads are defined correctly. So you just see that for two sides, you'll have to use according to local surface system. And then for the other alternate sides, you're going to use opposite to local surface system. And then once you're done with that, just apply and close. So that is how you load them. Okay, then I'll press on exit and then proceed to the other bit. So at this point, you've already ensured that our software or our structure has no errors. All right. So now that we have done that, the next thing that I would want us to do is to replicate these floors upwards. And then at this point, we are only replicating story number 2. We do not need to replicate the basement floor. This one is just a unique floor. The story number 2 is there. The story number 2 is the typical flow, and it is typical by say just 4 times. Okay, so to do that, we are going to do this by going to story 2 here, and then place your cursor on stories and go to copy story. Okay, so just to repeat this, you go to story here, right click, place your cursor on stories, and then go to copy story. And then you have the option to do this multiple times. Okay, so you ensure that the height is your floor height 3 meters, and then it is going above. So above, it's going to the top, so ensure it's above. And then now in the number of operations, I recommend you work one at a time. so that it is not too heavy on your software. And then once you have one, you go to the top floor here, stories. You uncheck filter stories, then right click, a copy story, you copy it once. All right, then the last one. Remember, you are not copying story number 3 now. The topmost story here is story number 4. So you go to story number 4, you right click, stories, uncheck filter stories, then right click again, stories, copy story, and you copy it once. And by doing that, you easily have your structure now modeled. All right, that is the easiest way to do that. Then before we proceed now, we may want, if you want to have a parapet level, say you want to have the region where, say the wall goes upwards or just the staircase cover, you can do that in a really easy manner. So for that one, I will do this. I will do this. So I want to define, will I get access to, let me see if I can quickly access my materials. Let me see, okay. Where are they stored? Okay, so I was just looking for the architectural files. I seem to find them. I found them, so luckily. So someone may want to model this part here. So at the moment we've modeled up to this part here. So if you want to model this part here, you can also do that. So to do that is really easy. So how you model that part is you go to story definition here. Okay, so you're going to define a story, just a simple story. You're going to add it manually. So add manually, and then ensure the reference level is the highest level. So story number 5, and then you click on add, and then apply. So once you do that, if you go to your 3D model, you're going to see that you have an empty story. Then to copy the columns that you would want to copy them to that point, just go to the plan view, and then go to the highest story that has materials. So at this point, that is story number 5. So you just go to story number 5, okay, slowly. And then once you are in story number 5, let me remove the meshing. So once you are in story number 5, this is what I want to copy. I want to copy these materials here where I have my staircase, and then I would also want to copy my walls, so that I can model that staircase cover. So this staircase cover is just this part here. Let me see where that is. It's just this part here. Okay, this part here. This one is the one that we are trying to model. All right. So this part here, the staircase cover and the lift core cover, is the part that we want to model. Okay. So to do that, I'll just select my walls and my columns. So I have this one here. I'll also have this one going to that level. I will zoom in, select that column. I'm pressing Control to ensure that they are not unselected. Ensure you press Control to ensure that those columns are not unselected. Select this column here, that column there, and then I can select this column here, and then I will just zoom in. Select my wall there, select my wall there, and select my wall there. So with that, I have all the members that I think are necessary. And once I have this, now I only want to copy these components. Upwards. So to do that, I will go to my stories in the object inspector. I have my stories. I will right click. And then once I go to stories, This time I will not copy story, I will copy contents of the story. So when you are interested in copying just specific elements, you use copy contents of the story. So select copy contents of the story. And then once you come here, ensure this option is checked. Perform operation on selected element stroke objects. So this will only copy the selected objects. So I'll just click on OK. Since it's checked. And then now once it is loaded and I go to my view plan, you can see, let me uncheck filter structure stories. You can see that I now have my vertical members for this flow. So with that, it becomes easy because all I have to do now is go to my plan view, go to my story 6, go to my story 6, and then model the walls for this, but the beams for this particular flow. So if you don't want to see these beams, remember we did this in the first week. If you don't want to see the lower flow, you just go to view, display, and then under favorites, you expand backgrounds, and then you uncheck lower story view. And then you click on apply and okay. And now you do not have that flow. Let me delete this so that I can model it afresh. So now I'll just model my beams. This should be easy for you. So I'll select beams, model them rather quickly. And then I will just start with these. Okay, I will start with these ones. And then I will also do this cantilever here. Okay, and then I think now with those I can now model the others say a bit faster. Remember how you are just modeling. I know you are now gurus at modeling, or I'd like to believe that. So I'll just proceed. Press escape once. Extend this to this point here and join it to that particular wall. Then do this there. Then extend, let me press escape first just to be sure. And then extend this there. And extend this here. Then I will extend that one there. And this one there. Then I'll press escape and model to this bit here. And here. Okay, and then I think I can tie these ones so that it's a bit simpler for me. And then once I have that, I'll just press escape. And then with that now, just a minute. With that now, I can model my panels. Okay, so to model my panels is going to be easy. Let me model my panels. So I'll just use the 175mm floor slab that we've been using. Ensure the model is shell, and then proceed to model them. Okay, I'll just proceed to model these. Being very careful with the direction of modeling. I know you now appreciate why we do that. I know you now appreciate why. And then
Hello, Captain.
hello.
Yes, at that our share was the lift cover. Can you hear me?
Pardon? Yes.
I said at the lift core wall, at the back of the lift core wall, I think we are not putting beam there.
I did a beam here already, so I don't need to do a beam here.
Okay.
Okay, so we have that. So with that, if I went to my 3D view, you can see now I have those elements there. So if you want to model that, you can be able to do that. All right. Then just to take you back to what we were discussing earlier in the class. So for those who probably joined later on, so when the class started, we tried to explain how we tried to give you a different view. So the first one is, if you look at most structures, this flat roof here, it usually does not have walls going up to story 6. It usually is just a small parapet wall. It's usually just a small parapet wall that you may want to consider at this particular point. Okay, so there's no need of you designing the structure with a wall at this point going up to story 6, because it's just going to be an over design. Okay, there's no the harm in doing that. It's going to be uneconomical, but it should not give you say it will not affect your structural integrity. But if you are keen with being, say, a bit economical, you can use a lesser load for this one. Then the other thing that you may want to do at this floor plan here is to ensure that these interior beams, because these beams are not going to be carrying any walls, it's going to be an open space. Probably you can have a few tanks, a few water tanks somewhere here. You could have some clotheslines somewhere there. So for this area here, we need it open. So we do not need to have it as, all these beams loaded. So the tricky bit here would be to load them differently, because we have copied the beams. Okay, but I just want to make your life a bit simpler. So this is how you do it. But before I model them, let me get to the question asked is that AD, by AD, how you turn off the mesh. So there are these options below the grid, below the global axis. The one on the farthest right, this one. If you can see my cursor, this is where you turn off the meshing. Okay, this is where you turn off the meshing or turn it on. So if you don't want to see it, just turn it off. I recommend once you're done with your meshing, just turn them off, so that your structure or your model is a bit easy to work with. Okay, and then at this point, just save your work multiple times, so that in case the software crashes, you do not need to redo a lot of things. Okay, just ensure you keep saving your work. And then once you do that, now I would want you to load your structure. So this is how you do it. This is how we say. This is how we all. Can I use edit? Yeah, I can use edit. This is how we edit the wall loads that have been applied to the beams on story 5. So again, where I'm circling my cursor, you can turn it on to see the soil loads, or to see the loads. So if you turn on the load symbols, okay, we have load symbols here. It is the third option from the right. These load symbols, if you can see them, please type a 1. If you can see the load symbol here, where I'm hovering with my cursor, please type a 1. Let me see 2 or 3 people type. Okay, so this is the one that we use. This one is the one that we use to see the load symbols. It's also a good way to identify if you have done all your loads. So if you just have it turned on and then you click on a load case, the software is just going to show you how that load case has been applied. So if you have a situation where you applied a load wrongly, say you did not use negative, and you checked this part, you're going to see that your load, these arrows, instead of pointing downwards, they're going to be pointing upwards. Okay, but this time, just to remain focused, I'm interested in the main wall loads. All right, so I want to edit the ones at the top. So how do we edit this? So before we edit them, let's run a simple calculation. Let's go to our loads. Let's calculate the loads that we need for that particular floor. So anyone willing to, what height should we use for our parapet wall? What height should we use for our parapet wall? I think 1 meter is just sufficient. So I'm going to use
1,000.
1.5 is too. 1.5 is too large. Probably
It's
1 or
too high.
1.2.
Okay.
It's usually around 900 if you look carefully. So we can use, let's go with 1.2 then. So we'll just use 1.2. And then we are going to multiply the 1.2 times 20 times 0.2, the thickness. And you're going to get 4.8 kilonewtons per meter. You can see it is almost, it's even less than half this load. So there is no need of having such an over design. So now what we do here is we edit these loads. So the first thing that I'm going to do is I'm going to select the beams at this level here. Okay, so I'm going to select them. I am going to select them. So I'm going to go to member selection. I want to select my main walls for story 5. Let me see if they're going to be selected. So if I go to group main wall beams, select them, okay. So you can remember, now this is why we were creating the groups. It becomes easier to handle. It becomes easier to handle, your structure. It becomes easier to work with. So you go to member selection, and then you go to the groups, the wall bearing groups. You click on them, okay, and then you go to geometry. And from this point here, you can filter out certain members. So I want to filter them out from, say, story 1 to story 4. I don't need them. So I'll have these as from story 1 to story 4. And then I'll click on the minus sign here. And once I do that, you're going to see that these loads here are no longer done what? They are no longer selected. Okay? They are no longer selected. So once I have that, I'll just copy the list. I'll just copy the list. Okay. Then once I copy the list, I'll close this and then press escape. Then I will click on this load here. I'll click on it twice, and then you're going to get this option to edit it. So this load here, let me have it in this level. You can see now we're in story 5. So I'll just click on this twice, and then we can have this. So I want to first have this as 0. Okay, I will change it to 0, and let me explain why. For the main walls that we selected, we still have some interior walls that we have, okay? We still have some interior walls, okay? Or let me explain before we go there. So for story number 5, okay? For story number 5, let me repeat how we select them. So we want to select our main wall bearing walls. So we went to member, group, wall bearing walls, clicked on the 2 arrows to select them. And then we went to geometry to filter out the beams from story 1 to story number 4. So you set them story 3 to story 1 to story 4, and then you click on the minus sign. All right. So these ones have been filtered out. But what we are remaining with here, you can see that we still have some interior beams here. Okay. So these beams are not going to be loaded at all, right? They're not going to be loaded. The beams that we are interested in are on this outer edge. So this is the reason why when I go to my view here and I click, okay, sorry. This is why when I go to my story here and I select these and I click twice on this load here, just click on it, any of them will work. So just click on this one twice in quick succession. I will change it first to 0, okay? And then I will click on add. And then once I click on add, this second option will appear. So for this one, you're going to go with the third option for the object selection. So this one now allows you to paste the members that you had copied. So we had copied the numbers for the beams on story 5. Then you click on OK. And now you're going to see that the main walls for this level here, they are not selected. you can see they are now not loaded. All right, they are now not loaded. Okay, I hope you can see that. You can see that they are now not loaded. Then I can select this one. Just press delete. Okay, I cannot delete them directly. So let's do the same thing. Let's do the same thing for the partition walls. The partition walls on this level do not need to be loaded at all. So let's select them. So what we do is we go to member selection over here. Okay, this is how you delete these loads at this level. You go to member selection over here. Okay, then you go to the groups you had created. You have partition walls. You click on the two arrows to select them. So by doing that, you're going to select the beams that are under partition walls. If I do this, you're going to see that they have been highlighted. Then you need to filter out these beams from story 1 to story 3 to story 4 because they are going to be loaded. These ones do not have any wall on them, so we do not need to load them. So I select partition walls, then I go to geometry. Then from Z-axis, you just select story 1 first. So you are filtering from story 1 to story 4. And then once you have that, you click on the minus sign. And then now you copy this. You copy this list here. So you just highlight it, then right click and copy. Then once you do that, you can press escape. You can press escape and then click twice on this load in quick succession. And then change it to 0 first. You can see the load is there, negative 7.65. We had calculated it earlier on. So have it as 0, then click on add. And then we go with option number 3. It allows us to enter the list. So paste the list and then apply. And then those loads are deleted. So we are together up to there. I hope so. So once you have that done, now go to your plan view in the story 5 definitely, and then select your outer beams. Okay, just go to your plan view and select your outer beams. Oh, where did that go? Okay, so once you do this, just copy this number here. Copy this number here, right click and copy. So just right click and copy it. Or you can, to be safe, you can just highlight the entire thing, right click and copy. Then once you're done, just press escape. Okay, press escape. Change the load list to say main wall loads. Then go to loads, load definition. We are going to do member, these are walls. So uniform load. And then the value was -4, -4.8. Then you click on add, and then in the apply to, you paste the list. Then you click on apply and close. Then now if you go to your view plan, you can see that the load has only been applied to those walls. Okay, so that's how easy it is to do. Then the other thing that I would want us to do is just to approximate the weight of a tank. Okay, the weight of loads from a tank. So how do we do that? So we are going to assume you're working with a 10,000 liter water tank, a plastic tank, right? So let's assume it's a 10,000 liter tank. So we are going to start with approximating the weight of the water. So if it's a 10,000 liter tank, we are going to divide that by 1,000 first so that we can get the volume in meters cubed, right? So if you divide 10,000 by 1,000, you should get around 10 meters cubed, all right? And then now we know, or from basic science, we know that mass is equals to density times volume, right? So to get the mass of this water, we multiply now the volume times the density. So it could work with 10,000 with 1,000 or 1,050, whatever works. So you just go with 10 times 1,000, you'll get something like 10,000. 10,000. Remember, this is in kilograms. Okay, remember this is in kilograms because the volume is in meters cubed and the density is in kilograms per meter cubed. So whatever value you get is mass in kilograms. Then now we need to turn this into a force. Okay, we need now to turn this into weight. So to turn it into weight, we multiply by the acceleration by gravity, right? So we just do 10, say 10,000 kilograms by, you can do 10 or 9.81. So I'll just go with 9.81. And then by going by 9.81, we should get a value like 9.81 times 10,000. That should equal around
98,100.
98,100. Okay. Then that is in newtons. So we can divide it by 1,000 to get kilonewtons.
98.1.
98.1 kilonewtons, right? So now that we have that, we need to convert it into an area load. So these 98 kilonewtons is not going to be acting on one part of the slab. It is going to be acting as an area load. So how do we get the area load? We are going to assume our tank has a diameter of 2.1 meters. Okay, we are going to assume the tank has a diameter of 2.1 meters. So you just divide this 98.1 by the diameter of the tank. I think the standard diameters for a 10,000 liter tank, they may differ from manufacturer to manufacturer, but I think 1.9 to 2.1 will suffice. So I'll go with 2.1. So 2.1, who will calculate the area for us?
And we're supposed to divide by the cross-sectional area of that, not just by the diameter, but by the cross-sectional area.
Yes, so I've just said you calculate the area, James. Why are you sleeping?
Like,
Yes, so you divide it by the area, not the diameter of the tank. You divide it by the area. So you should,
you said the diameter is 2 meters or 2.1.
you've gotten
Are we taking a diameter of 2 meters or 2.1 meters?
2.1 meters, or even 2 is just okay.
If we consider a diameter of 2, that is, the area would be pi d squared over 4. That will still be pi, because d squared will be 4 divided by 4, which is just pi, 3.14.
So, okay.
No, if we use diameter of 2.1 now, our result will be 28.35.
Will be
28.35.
okay. So we have a load of 28.35 kilonewtons per meter squared. You can see it's a very how do you say this? It's a very huge load that you need to consider, right? So we'll just consider that. So I'll go to my panels. I'll go to my plan view. And then I'll just go with the option we had earlier. I will just load some of the slabs with it. I'm not going to load the entire panel with it. I'm going to load just these top parts. All right. I could also load this and this. And then I will select them and then copy their numbers. Then I'll go to loads, load types. I can define these as live, and then I could add these as, say, the water tank load, and then click on add. then I'll close. I will go to now loads, load definition, and then it's a surface. You select the uniform planar load, you enter the value. So below, I think it was negative 28 points.
28.35.
Okay, you add, then you paste your, then you paste your list, and then you apply and close. And once you do that, you are good to go. So that's how easy that is. Then after you've done that, the next thing that you would need to do now is to, let's now define our wind loads, okay? Let's define our wind loads. So to define our wind loads should be really easy, because the first thing that we need to do is to just draw as a, how do we call this thing? We draw cladding to assist us in simulating walls where we have masonry walls. So in this position here, we are going to be having masonry walls. So we're going to draw a panel from this point here to this point here in story 5, and then to this bottom part here, and then in this direction here as well. And then we are only going to do this in 2 directions, only this side and this side alone. And the reason we are doing this is because you are only using it for wind simulation. You're only going to be using this for wind simulation. And we said you only need to do that in two adjacent directions. So this one, and we can do one in the orthogonal or in this direction here. So let's do that. This one should be simple. So what we do here, let me zoom in. So we are going to be working with cladding, and this is important. Please don't model a panel, model a cladding. The cladding does not have any weight, and it's not going to affect your analysis. So you model the cladding, you go to geometry, and then you click on cladding. Then you select rectangle, and then you click on this point here, and then this point here on the end. And then once you do that, once you click on those 2 points, go down to story 1. Okay, you go down to story 1, and then you click on this end here. And then if you do that, you're going to notice that you have easily modeled the cladding on that part. The other way of doing this one may be a bit difficult, especially when the outline of the structure is a bit complicated. So it may be easy for this one, but for some structures, it may prove difficult. So in this method, you click on the top part, this one, this end part, and then this one. It's the same thing that you are doing, only that now you are doing it in the 3D view. All right. Then once you have those panels, we can now do our analysis or our wind simulation. So to do our wind simulation, you go to loads, and then you go to wind load simulation. All right. So to define or to simulate our winds, we go to loads, and then we do wind load simulation. You click on generate wind loads, and then all you need to do now, this one is simple, select the directions. You can select the 3 of them. And then select the directions in which you modeled your panels. So I had mine on the left and on this direction. That's why I'm selecting this. And then in the wind velocity, you're going to get this in your wind maps. So I'm going to do this as 30, or you could just do a quick Google search and see, say the worst case winds that you would expect in a certain area. And then after you do this, all you need to do is click on start and give the software a bit of time to load this. Okay. So as we wait, let me take some water as we wait.
Captain, I see. Okay,
Okay, so it is done. It's quite fast. It is quite fast. So with that, all you need to do is close and then now proceed. Favor, yes, you can check. Is it Eurocode 19? We have another code. We have the updated code in Eurocode. I'll share it in the Telegram channel. You can have a look at it and then compare it with the CP3. But the latest one is in Europe, is part of the Eurocode series. I've just forgotten which are the specific number. Okay, so once you do that, you're going to have defined your or gotten your wind loads. And then after you do that, you're going to get the combinations here. All right. So at this point, I think we have all the combinations that we need. We have all the loads that we need. The next thing that we would need to do is to combine our loads. Okay. So it is important to remember there is no point in life where this load with this structure here is going to be exposed to one load type alone. That does not exist. So we need to combine our loads. So we're going to be doing the ULS combinations and the SLS combinations. So to do that, it's really easy. All you need to do is go to loads and then you go to manual combinations. So I prefer to use the manual combinations. So you go to manual combinations and then you define your combination. So to define the loads, you go to loads and then you go to manual combinations. So let's start with the ULS combinations. So we're going to start with the ULS combination. So let's call this ULS combination with no wind, okay? So that we can have a design or we can see the results without the influence of wind. So I could have one ULS combination, no wind, and then click on OK. And then once I click on OK, I'm going to be taken to these combinations here. So at this point, all I need to do is select the load cases that I need. So I'm not selecting any wind loads. So I'm just selecting the gravity loads. I'm just selecting the gravity loads and then assuming the others. Okay. So select the gravity loads and then you push them to this other end using this arrow here. And then once you do that, you're going to see that they are assigned the correct factor. Then you click on apply. Okay, so you just click on apply and then that load case has been added. Then we are going to create we are going to create 3 more wind load cases or ULS cases. We are going to include a ULS case with all these gravity loads, and then we are going to do we are going to include one wind direction at a time so that we can get the worst case scenario for each wind direction. So you're going to do that. You go to new ULS. So you say, let's start with X plus. So we're going to say ULS plus wind in the X positive direction. So you just do ULS plus wind in the X positive direction and you click on OK. And then once you do that, now you have to define the loads that you need. So I'm going to click on the number, press Ctrl to select first my gravity loads. Okay. Select your gravity loads plus the soil loads. And then now you select the X plus direction. So this is the X plus direction. So you push them toward them. So you can see you added one wind direction. Then you click on apply. And then once you click on apply, you just click on new to define a new one. So we're going to do another wind direction, ULS, then plus the other direction, X plus and Y plus, the orthogonal direction. And then you click on OK to define them. So you start by selecting your gravity loads and then the interested wind direction, and you add it in this direction here. So you just ensure it is there are those gravity loads and then this wind. Then you click on apply. Once you click on apply, you click on new to define the other the other wind load. So this time it is ULS plus the wind in y direction. So what this will do is it will allow us to see the worst combination between the gravity loads and the wind loads in a given direction. Okay, so y plus is that, then you add them and you apply. So by doing that, now we have all the ULS combinations that we need. Then the next thing that we need to do is add a new combination. And then this time we are going to add the serviceability limit combination. So you're going to change the combination type under this point. Click on ULS and then click on SLS. So just click on this drop down and then you click on SLS. And then you give it a name. So you have SLS combination. And then for the SLS, we only need it for the gravity load. So you just click on SLS, click on OK. And then once you click on OK, you just select your gravity loads and you just select your gravity loads and then you add them. And then you can see the factor is 1. And then once you have that, you just click on apply. You just click on apply and close. And by doing that, you have your load combinations. So to confirm you have created your load combinations, you just go to loads again and you go to combination table. And then at this point, you can be able to see all the combinations that you have created. So you can see the load case, then add the list. So this one are these numbers here. You can see the number of the load. So 1, 2, you can see where they are. You can be able to tell that your dead loads have been added correctly and your live loads have also been multiplied with the or by the correct load or by the correct factor. And then once you have your loads created correctly, you just click on this to go back to the geometry layout. And then now we can do our analysis. So running the analysis is quite easy because all you have to do is go to analysis and then you start with analysis types. All right. So once you start with analysis types, so here we can define the type of analysis we have. We have different types of analysis types. So we have let me show you. We have the linear and then nonlinear analysis types. So for structures that are going to be exposed to lateral loads, we always recommend you go with a P delta analysis because it's more accurate and it's going to factor in the secondary movements that arise from the lateral loads. Okay. So for that, we are going to select our ULS combinations and change the analysis types from the linear combination to the P delta analysis. So to do that, all you have to do is go to this option here. You can see the operations on selection of cases. You click on these 3 dots and then you go to combinations. You can select all your combinations and list them up there. And then click on close. The numbers are going to appear here. Then click on change analysis types and change it to P delta. Then click on OK. Then once you click on OK, we're going to see that they have been changed from linear to combination to nonlinear combination. And then once you have that, all you need to do is run your calculation. So you may find a few errors here and there. So we are going to try and fix them. So just let it run. So if you get a few errors, just let it run and then you're going to fix them. So just give it a minute to complete and we should be good to go. So it may take a bit of time depending on how, on the nature of your laptop, also the type of structure. So if your structure is quite large, it may take a few minutes, probably almost up to 5-10 minutes if the structure is very large. And then for smaller structures, it is quite fast, it may take even less than a minute. So the time of analysis depends on the type of structure. Okay. So just let it run. Let it run and they should be good to go. So at this point, it's just doing the static analysis for the individual loads. And then in a few, it's going to start doing the P delta analysis, P delta analysis for the combinations. And then if you look at the top where I have my cursor, you can see the software is telling you that it is during analysis, and it's also during analysis here. So I'll just give it like a few minutes to run, and then you're going to proceed from there.
Hello, Captain.
Hello.
Yeah. Considering the soil load at the
Yeah.
foundation,
Yeah.
yes, I'm a bit confused. So I want you to share more light to it again, please. It's because in the basement now, we are
Yeah.
we are going to fill the space with soil. Now, when we fill the space with soil now, the soil will be acting, the the active pressure will be horizontally, which is from inside the base to outside of the wall. But now when you see the load symbol of how the varying load is being applied now, it's like the varying load is acting from the outside, is pushing the wall inside. It's not towards
I, I
the
I think you got it. I think you got it wrong, engineer. Because if you look at the purpose of these specific walls that we have, this is our
yeah.
basement here. We are not filling the basement with soil. The soil is on the outside. So the soil is pushing the basement wall inside. There's no soil
Okay,
here. This
okay,
wall
okay.
is
Now
this is to resist soil from going into the basement.
understood, understood. Thank you.
Super.
Yeah, the basement is actually extra parking space.
Yeah. So this usually takes a bit of time. This usually takes just a bit of time. Our structure is, say, significantly large, and then we also have a couple of combinations. So the more the combinations, the longer it takes. So just be patient with it and let it run, and you should be good to go. So let's wait.
Captain Gatim, as we wait,
Yes.
I noticed that when it came to the load combinations,
Yeah.
the we only did combinations with only one wind type, X plus Y, then one with Y. But we
Yeah.
didn't do those with with two wind directions. Why is that?
You actually missed it. I did all of them. I did the X plus, the Y plus, and also this direction. Then
Yes, but what I'm
if
saying is I would have
yeah,
expected, like, why didn't we do, yes, that
it's a,
bit
co-
I saw.
a combined
Yeah,
one.
but why didn't we do one where you have X and say the one which is like X plus Y? Because wind is very erratic, it can blow in any direction.
Okay, so the reason is this: wind actually rarely blows in two directions at the same time. Okay, so our main direction is this one. So we have a load case for this one, and then we have a load case for this one. And then just to counter the situation where it may be somehow acting on both directions, which is rare, so we included this direction as well. Do you see the direction that we called x plus y plus?
Yes,
It is
that
blowing in
one.
this
I
direction.
understood. Yes, it's to cater
So
for that, like
it's more of a
45
combination
degrees.
of both directions.
Yeah, so for me, I was imagining a situation where you have wind blowing in the X and saying the X plus Y.
Wind blowing in this direction and this direction.
You're blowing in the X and say the X plus Y.
So x plus y is this, and then
Yes,
x
I know you
direction is
put a
this.
caveat by saying that yes, you put a caveat by saying that wind rarely blows in two directions at the same time. But I was trying to imagine a scenario where you have wind blowing in both, say, the x direction and the x plus y direction.
Okay. And then if you're just curious, the beauty is that you're not going to be doing the calculation manually. You could just
Because
create a
my
load
understanding is that
configuration and
wind
then
will
see how
come
it
from anywhere.
behaves. Yes, it will come from anywhere, and that's why we are designing for the worst case scenario. So we have a combination for each direction, and then our worst case scenario is going to be used to design the entire structure. Do you get it, engineer?
Let him first come again.
So my understanding, you said, is it doesn't hurt for me to create an extra combination with that, right?
Yeah, it doesn't hurt.
Just to see, since we are not doing using pen and paper, since we are not doing the
Yeah.
calculations using pen and paper, okay, that's fine.
Okay,
But
but
I
I
also
still
get
did
your
not understand.
understanding of why you chose. What I was saying is, we have the x direction, we have the y, and we have the x plus y, which
Yes.
are like three directions of wind. So
Yeah.
in our manual combinations, we did one of the dead loads plus the x, one of the dead loads plus the y, and one of the dead loads plus the x and y. So I was saying,
Yes.
I noticed that we didn't do one where you have those dead loads and say the x plus the x plus y. But yeah, from what you've said, I could try as many combinations as I want.
Okay. Engineer Alan, do you have something to add to that?
No, okay. Yeah, just to categorically state that whenever you are considering wind loads, you consider them on one direction where the highest direction of wind is expected. So usually how you determine this is the location of the structure vis-a-vis where wind is coming from. And usually the most influences of wind energy is the water bodies. Okay? So that's why you find that when you are doing those like wind energy analysis, so you find structures, those ones, especially those in Kenya, Tanzania, because of that, their closeness to the Indian Ocean, they tend to have higher values for wind energy. And it is, you consider one direction. Okay, it's not that you are going to consider like two directions at the core. You only consider two directions when you are trying to make comparison. The comparison in this matter, for example, if you are saying that you want to consider x, y, okay, then you also want to consider maybe y, z. So you will check and okay, this one you do like manual analysis. Then when you get the one with the highest figure, it is the one you use to make sure that the other one is also put into consideration. So the highest figure usually just gives like factor of safety, that in case the wind energy comes and this is the highest energy that I'm expecting, my building will be safe.
So it's not that you are going to consider two directions at a go. It's one direction at a time, then you'll pick the highest value that you'll use in your analysis. So it will also, of course, helps you with the issues of seismic and what, because seismic for it comes in all directions, X, Y, Z. You see that? So that's why they usually pick the highest value, and it's on one direction only. Thank you.
Captain, he's actually triggered my mind. There, in those parts of the world, like in, say, Florida in the US or the Caribbean, where they have tornadoes, it's like you have winds coming in opposite direction, then they meet to cause that cyclic kind of loading, kind of like twisting load. So, how would you handle that? Because it's easy to think that they'll cancel out, but they end up causing rotation. And I've seen cases where just wind, no rain, no nothing, just wind blows away a reinforced concrete structure and only the substructure remains. So that is where I was coming from, that how about a situation where you consider both, or how do you design for tornadoes in robot?
Hello, engineer. Word on that. Sorry, Alan. Let me just weigh in on that. So there's something that is called a wind tunnel simulation. So if you are doing very, say, tall structures, or you are in an environment that is that extreme, you would have to do a wind tunnel simulation. They are rather expensive because you have to have like you have to have a very, say, specialized personnel to do that. And then once you do the wind tunnel simulation, you include the results here. So instead of you using the generate wind loads, you use the second option. But for us, the first option is always or almost always sufficient.
It's sufficient because of our region. But
Yeah.
according to this question, that's when you bring that expertise.
Okay. So
Luanga, are you satisfied?
Yes, I just saw CFD. What is CFD? In the second option, it had something similar to CFD. What does CFD stand for?
Alan,
Just
are you in a
yes.
position? It stands
What
for
was-
computational fluid dynamics. It's what is used in the wind tunnel analysis.
Luanga, now, okay, that analysis Gatim is saying, yeah? But for it, it has like a specialist something. There's some specialist who gives you those things. So you bring those values and you input. That's when you use that CFD thing. You get it?
Yes, makes a lot of sense. I've actually
Oh.
watched it on some those documentaries like B1M or Extreme Engineering, where they build like models and go to wind labs and try different forces of wind and see how the structure behaves. It's also common. I think I've seen it when they are building some of those very tall bridges to see how
Yeah.
the bridge will actually react to
Yeah.
the wind loads. Yes, so makes a lot of sense.
Especially
Thank you.
those ones in China, then
Yeah.
that badge
Yes,
Yeah,
yes, true.
it's also quite common for F1 fans. It's also quite common in cars. I think for
Yeah.
most cars, even before we get to use them, they undergo such analysis. But it's very expensive, and you would
Expensive
probably
analysis.
not find it on this
Mm.
in this part of the
Of
world.
Africa.
So that's how you do your analysis. Alan, am I audible? Please confirm.
Yes, very audible.
Thank you. So that's how you do your analysis. Once your analysis is done, you're going to get the results for finite element for the FEM are available. And with this, now you can go to your results and view them. I'm not going to go into the results at this point. Engineer Abraham is going to have a full session on that on Saturday. So I really welcome you to that session, or invite you to that session. And then also the errors that have occurred. I think we only have one error. We have shown you how to how to get rid of this, but it's also going to be tackled in the next session. Okay. So thank you for showing
Captain,
up for
Captain,
this
Captain,
class.
Captain, Captain. Hello, Captain.
Could you let me finish
Hello,
first and then I'll give you the opportunity?
okay.
Bello, is that okay? Can I finish first what I was saying?
Yes, you can finish. You can finish.
Okay. So thank you everyone for joining us tonight. And I look forward to seeing you in the next class on Saturday. So next week we are going to have 3 classes as usual. On Tuesday, that is on the 16th, then on Thursday, the 18th, and then on 20th, we are going to have a vote. Some of us may travel up country where they may not have, sufficient network. So we are going to have a vote with regards to that, and then see if we are going to have a class then. And then from there, we are going to take a break, and we are going to return in the new year, probably date 5 or date 6, and we're going to proceed with the course from between date 6 to date 17th so that we can proceed, so that we can finish it. We do not want to rush you so that we can do everything slowly so that it can be of benefit for you. Okay? And you'll also get time to relax and also probably redo everything in the time that you're going to be free. All right. So I hope that is okay with everyone. I hope that's okay with you. If you have any queries, just text me and we are going to see how we can tackle them. All right,
It's
so
okay with
Bello,
me.
Captain,
Hello.
yes,
yeah, my question is,
I also
let's have one person at a time. Let's not be chaotic, please. So Bello, go
oh
first and then the
okay,
next
it's okay.
person will
Let
go
Bello go
next.
first. Let Bello go first.
okay, thank
All
you.
right.
Thank you. Yeah, my question is, if we are considering the roof, now we are having a pitch roof now, and we have a
Yeah,
roof beam. So
yeah.
now, is there a code that you can recommend for us how to calculate the dead load of the roof so that it will be imposed on the beam?
You can actually model the truss here. You could model your trusses here, but I don't have a very specific formula to approximate the dead load of the trusses. I'd have to
Okay.
check that and then get back to you. Or unless someone
Oh,
has a formula that they can suggest, would welcome it.
okay.
Okay.
Herbert?
Thank you. Just to add on what Bello has said, maybe as we move on, you'll help us with a roof that is not flat like this. That is so that we are able to see how to simulate the loads. Then lastly, I looked at this is not for this class now. I looked at your calendar of 2026 and
Yes.
I saw you incorporated you incorporated Revit for steel. Is it possible to
Yes.
also do the same with robot for steel structures?
Yes. If you actually look, yes, we have one for steel structures. It's actually the month before Revit. So you're going to start with the design and then the detailing.
There is robot for steel. Maybe I missed it. Okay, it's okay. I'll
Yeah.
look through
Yeah.
it again.
Guys, no worries. You could just have a look and then if you miss it, just reach out to me.
Okay, Karen, thank you so much.
Super. So thank you, everybody. Have a good night
Captain,
and
one
see you
small question
tomorrow.
before we go.
Yes.
Yes, so when we were doing Revit, one of the things that